Hi, everyone. Like I said in the previous videos, it helps to be familiar with these identities over here and their various pieces. Now, it may also be helpful to mind dump these early on in an exam. By a mind dump, I mean you write them out quickly on some scratch paper or on the back of your test. That's not cheating, assuming that you have gotten the test already and the instructor says you can start. So let's see if you can recognize this form here. Imagine a substitution, like a snap substitution. Tangent of 25 degrees, let's say that's u, plus tangent of 20 degrees, let's say that's v, all over 1 minus tangent of 25 degrees, or u, times tangent of 20 degrees, or v. Now, does this sound familiar? Tangent of u plus tangent of v, all over 1 minus tangent of u, tangent of v. That sounds to me like the sum over 1 minus the product. And I hope that sounds familiar. That's going to be overall a sum identity for tangent. So here's the identity that we're using. Tangent of u plus v equals the sum, tangent of u plus tangent of v, over 1 minus tangent of u, tangent of v. And this identity will help us because all the way up here, we don't know the exact values of tangent of 25 degrees and tangent of 20 degrees. I know these values are positive. I know that this is bigger than that. And I know that they're going to be less than the tangent of 30 degrees, say, but I don't know their exact values. It turns out the sum identity will help us. And we're actually applying this identity from right to left. That's why I'm telling you that it's important to be able to recognize when an identity might be useful, or at least be prepared to look over the list of identities you've mind dumped on your exam. So when you see this, especially if you think of a snap substitution, well, think about this form and you might realize, aha, this is the right-hand side for the sum identity for tangent. So let's apply this identity backwards, right to left. In fact, I'll write it in reverse. All right, well, u was 25 degrees. V was 20 degrees. Okay, same for down here. And you can see here that when we do that, I'm just rewriting the given expression over here. All right, so if you want to call this thing star, right, I'm basically telling you that star is equal to tangent of 25 degrees plus 20 degrees. U is 25 degrees, V is 20 degrees. Okay, so what is U plus V? What is 25 degrees plus 20 degrees? It is 45 degrees. And I hope you know, either from the unit circle or a table, that when you consider the 45-degree angle, the slope of this terminal side is 1. The tangent of 45 degrees is 1. That's a great special fact. So all of this big old mess over here, it turns out to be 1. In fact, your calculator might be a little bit off. Your calculator might say something like 0.9999 whatever because of rounding error. Actually, this is exactly 1, right on the dot. This is great for a placement exam problem. This is the kind of problem they love to put on a placement exam. Like if you're entering university, great problem they would put on a placement exam. Okay. Now let's simplify a more general trig expression in theta. Simplify 1 over sine of 3 theta cosine of 3 theta. And actually, I'm going to show you a solution that's probably clearer than what I have in my notes. So it's good to attend lecture. Let's take a look at this. Let's perform a substitution because we have these matching pieces over here. Let's let u be 3 theta. Then we can rewrite this as 1 over sine of u cosine of u. Right off the bat, this looks more comforting to us. And let's look at the bottom here. Well, you might look at this and you might go, well, I guess I could rewrite this as cosecant of u, secant of u. That's true, but we're going to try to get something more compact. Look down here, sine of u, cosine of u. What trig identity has that as a major part of it? In fact, let's try to go to our list of identities here. Let's see, the product. Sine of u times cosine of u. Look at these right-hand sides. A product. Sine of u times cosine of u. Almost all alone, maybe. Oh, Ooh, look at this here. Interesting. Sine of 2u equals 2 sine of u cosine of u. Some students might say, but hey, there's a 2 in front. I can't use this. Well, you might be able to do some massaging, do some modifications. We can try to use this. In my notes, I use the fact that sine of u cosine of u is 1/2 sine of 2u. That's one way of looking at it. But here, I'm going to try a different approach. I will use this double angle identity for sine, right? It's the double angle identity for sine. Let's use this, but in a different way. Okay, so in order to apply the identity, it would be very helpful if I had a 2 in front of sine of u cosine of u in the bottom, the denominator. Well, let's go ahead and insert a 2 as a factor. But wait, you can't just put in pieces because you feel like it. You have to pay for them somehow. Is there an easy way to pay for multiplying the bottom by 2? Well, yes, there is. Multiply the top by 2. And that is legal because all we're doing is multiplying by 1. We're basically multiplying by 2 over 2. And again, we want to multiply by 2 down here because then we're going to make the bottom look more like a part of a known identity. What is 2 sine of u cosine of u? It's the right-hand side of our trig identity, this double angle identity over here. So I can substitute 2 sine of u cosine of u outright by sine of 2u. We get the 2 on top over. The bottom then becomes, much more simply, sine of 2u. And we've really shrunk this thing down. But we're not done yet. There are a couple more things we can do. First of all, we try to avoid fractions where possible. So what is the reciprocal of sine of 2u? As far as the 2 goes, remember the 2 we can pop out in front. Okay, remember, it is legal to pop a factor of the top out on the outside. If the 2 are on the bottom, we'd have to pop out a 1/2. But the 2 is on top, so we can pop it out, and then a 1 is left on top here. Do not forget the 1 up here. I should put this in red. When the 2 pops out, it does leave behind a 1. Okay, you still have a fraction here. Now, what is the reciprocal of sine of 2u? It is not secant of 2u, it's cosecant of 2u. So we've made this look a lot nicer. 2 cosecant of 2u. But wait, are we done? Are we done? This looks very nice, but remember, it's in terms of u. And u is our creation. It was used to help us out. But the given expression was in theta. So if your friend gives you an expression and tells you to simplify it, and you leave this thing in u, your friend's going to ask, well, what the heck is u? U is 3 theta. You better plug that back in. Substitute back. U was 3 theta. And then in the argument here for cosecant, what is twice 3 theta? Remember, it's a double angle identity. Well, here, right, and then we move over here. We have cosecant of 2u. Okay, cosecant of twice 3 theta. Twice 3 theta is 6 theta. And you can delete the dot there. 2 cosecant of 6 theta, that looks very good. You really couldn't do any better than that for this expression. So that big ugly thing at the beginning, 1 over sine of 3 theta cosine of 3 theta. For example, in calculus, you'd be very irritated if you have to take the derivative or integral of this. But if you simplify this down to here, okay, this is much easier to differentiate, that is, take the derivative of or integrate. 2 cosecant of 6 theta. Remember, simplifying can really be your friend in both pre-calculus and in calculus. Simplification is often your friend. you help yourself by rewriting this ugly thing as 2 cosecant of 6 theta. So I think that's a clearer way of expressing the solution. Now, in my notes, my solution is correct, but I think it's harder. So for example, here I tell people, okay, recognize you have a double angle identity in play, all right? If we had a 2 in front, we'd have sine of 6 theta, right? Twice 3 theta. And then if you divide both sides by 2, basically what I'm doing here, I'm adopting the strategy of solving for this thing in here. I want to actively substitute that. And I substitute it by 1/2 sine of 6 theta. When you do that, the reciprocal of 1/2 is 2. The reciprocal of sine of 6 theta is cosecant of 6 theta, which we got before, right? And this solution works, but I think it's harder because then here I didn't really use a substitution very well. I could have let u be 3 theta. And I think this is kind of harder to understand. Whereas my method that I just showed you, okay, which involved making something look like the form you want to see, right? So you're kind of engaging in wishful thinking. It's okay to engage in wishful thinking if you compensate, if you pay for it appropriately. Here, it's okay to compensate. It's okay to pay for multiplying the bottom by 2 if you do what? If you multiply the top by 2. That's legal. So that's a case where wishful thinking can be made legitimate if you compensate or pay for this accordingly in a legitimate way. But make sure it's legitimate. For example, you could not add 2 to the top and the bottom. That's not a legal move. You can, however, multiply the top and the bottom by 2. That's like a compensation idea. We talked about this in, I believe, 0.10. Make something look like the way you want it to look. We can apply the identity immediately. You pay for what you did. Next up, oh, well, before we start solving equations, a comment. In chapter 4, I had you look at identities like these, where you look at something like this, right? And you consider the unit circle. Consider the unit circle. Assume for now that theta is acute, although you can run an animation in your head and imagine theta changing. If theta is in quadrant 1, where's theta plus pi? What quadrant's that in? Theta plus pi is in quadrant 3. Now, how does the sine of theta plus pi, how does the sine value for this angle correspond to the sine, relate to the sine value for this angle? Are they equal, opposites? What are they? Sine of theta plus pi versus sine of theta. How do the y coordinates, sine value is y coordinate, remember? On the unit circle. The sine value is the y coordinate on the unit circle. How does the y coordinate of this point compare to the y coordinate of this point? In fact, even if you change theta, theta could be any real number of radians. If you consider the sine of theta versus the sine of theta plus pi, how are the sine values always related? They are always opposites. For example, these y coordinates here are opposites. The sine of theta plus pi is the opposite of sine of theta. So you may have conjectured something like that based on chapter 4. But now in chapter 5, guess what? We can verify this. We can prove this conjecture and make it a bona fide theorem. By using what identity? The sum identity for sine. Try it out. Try it out. And you'll see stuff like this on the homework. It falls through very quickly, meaning it works out very quickly. Next up, we're going to solve equations using these additional identities.